So up until this point, we've talked about where the image would be located and how it would be reflected depending on where the object was located. But we can actually use an equation to find the exact measurable distance of the image and of the object. So that's known as the mirror equation, which is this one right here. Now, this dO stands for the distance of the object, this dI stands for the distance of the image, and the F is referring to the focal length. So I'm just going to run through this problem so you know what to put in for each of the variables. So it asks us to locate the image formed by a concave mirror whose focal length is 10 centimeters if the object is 35 centimeters from the mirror. So using my mirror equation, I plug in the length they give us for the focal length there, where F is, and I also plug in the object distance for dO, and I solve for dI, which is the image distance. Just be careful that you don't get them messed up. The wording will be exactly the same every time, so if you're looking for the image or image distance, it will say image formed or just the image distance, and if you're looking for the object, it will say. We have these two equations involving the height of the image and its magnification. So if you notice in this equation here, there's a negative sign. It's very important that you don't accidentally omit that when you're doing your problems. The sign maintains the correct sign relationships. So if you have to remember that anything that's located in front of the mirror is considered a real image, and anything behind it is a virtual image. So if you go back to cases 2, 3, and 4, where we only had real images, the distance that it was located from the mirror was positive because it was on this side of the mirror. So the distance is positive, but its image was always inverted, so the height was negative. Now, for the virtual images, its distance is going to be negative because it's going this way or behind the mirror, but its height will be positive because it was erect, and I believe that was case 6. And then lastly, if you're asked to find the magnification, that would just be the absolute value of the height of the image and the height of the object. So this one's pretty straightforward. So lastly, let's talk about how we find image distance, object distance, and the image height with a convex mirror. So far we only touched on concave mirrors, but you'll find that it's pretty much the same. So remember, the rules for the rays are slightly modified just because of how things are reflected in a convex mirror. So first, an incoming ray that is parallel to the axis has a reflection that, if you extend it back, looks like it's going through the focal point. So the basic definition of a P ray is still the same. It is an incident ray that is parallel to the principal axis and reflected through the focal point. Only with a convex mirror, the rays don't converge out here. It just appears as though they come from that same point behind the mirror. So if I were to extend this reflective ray, it would appear like it was going through the focal point. Second, an incoming ray that would appear like if it was going through the focal point, if it were extended, would reflect parallel to the principal axis. That's the F ray. And so convex mirrors are pretty easy because they can only produce one type of image. If you see here, the image is always going to be virtual, meaning it's behind the mirror, and it's going to be smaller than the object. Now keep in mind, when you're using the mirror equation for convex mirrors, the image distance is always going to be negative because it's on this side, and so is the focal length because it's also measuring the length from the mirror to here. Remember, the focal length in a convex mirror is located behind the mirror because the image looks like it's coming from behind the mirror. And as far as the magnification that equation works as well. So let's just go through this problem really quickly so you understand where you need to put in that negative sign. So if we're looking at an image, locate the image of a 2 centimeter object that is 10 centimeters from a convex mirror whose focal length is 10 centimeters. How high is the image? So that at the end is asking for its height. So in order to find the image distance, I plug in DO, or the object distance there, but notice that DO is going to be positive because the object is in front of the mirror, but the focal point, or focal length, is negative because the focus or focal point is behind the mirror. So the distance from the mirror to the focal point is negative. And so you would go about the same process as you would before, just being careful to put in the negative signs. And then using the image distance that you found, you can solve for the image height using the equation that relates each of the two. And notice again, it's important that you keep the negative and you keep the negative here so that you can get the correct sign of the height here, which is positive, because we know if the image is virtual, then it's always going to have positive height because it's upward.